Hello. If you're new to C programming or you've never really used C programming down at a low level to manipulate bits within a register, then you've probably never dealt with bitwise operations in C programming. If that's the case, that's what this video is all about, and I'm going to be talking about bitwise manipulation in layman's terms that hopefully everyone can understand. Let's get stuck in, shall we? So here I'm going to be using a set of household lights, essentially, what we're starting off with here to keep things simple. So here you can see I've got a light in the kitchen, the dining room, living room, hall, landing, bedroom 1, 2 and 3. And here they're represented by switch states, so you can see all the lights are off at the moment. So these are on-off switches, and saying on or off is the same as saying true or false, or 1 or 0. So 0 is false, it's off. The switch is off, the light is off, it's a false state, or a 1 is the same as true or on, so it would be 1 or on. So let's switch on some of these switches and have a look at what we've got. So here I've switched on a few of the switches. I've switched on the dining room here, you can see the lights come on, the hall light here was switched on, the landing light switched on, and bedroom 2 was switched on. Now, as well as viewing these as switches, we can also view them as logic states. So we've got the same state here, like we have here with 1s and 0s. So this switch is off, so it's represented by a 0 here. This switch is on, so it's represented by a 1, and so on. Off, 0, on, 1, on, 1, off, 0, on, 1, off, 0. And this we can view as a binary number. So we have the binary number here, 0, 1, 0, 1, 1, 0, 1, 0. That's the number there. Each of the 1s in that binary number represent a light that's on, and each of the 0s represent a light that is off. Now we can also represent this number in decimal. For example, I've put the values of each of the bit positions up here. So as we know, the least significant bit in binary has a value of 1, and then it doubles up each time to 2, 4, 8, 16, 32, 64 and 128. So for example, with this binary number here, we've got the number 64, 16, 8 and 2. And if we add all those numbers up, we get to the decimal number 90. And that can also be expressed in hexadecimal as 5A. So that gives us the current state of all the lights in a single number, either binary, hexadecimal or decimal. So the next thing that we're going to do is we're going to OR in another value. So we've got this value here, the hexadecimal 5A that we spoke about before, and now we're going to do a bitwise OR operation. And what this is basically doing is it's forcing bits on. So any bit in this byte here that we're going to OR into this byte here, any bit down here that is set will cause the bit above it to be set as well. So this is a bitwise operation, so when we OR these two values together, each bit is ORed together in turn. So with an OR, two input OR gate, you would need one of the inputs to be true for the output to be true as well. The only way you'll get a false output is if both inputs are false or zeros. So for the first least significant bit here, we can see we've got a 0 and a 0. So the resulting bit value that's going to go in here is a 0. That's the result of an OR with two false inputs or two 0 inputs. This one here has already got a 1 in this bit position, and there's a 0 down here, so we OR those together, we will still end up with a 1 in this bit position here. Here we've got a 0 and a 0, so that will end up as a 0. Here we've got a 1 and a 0, so this 1, this 0 equals a 1, no change to the state here. Again, we've got a 1 and a 0 here, so that will stay as a 1. Here we've got a 0 here and a 1 here. So a 0 and a 1 through an OR gate will be a 1. So this value here will change from a 0 to a 1 when we perform this bitwise OR operation. Again, we've got a 1 and a 0 here, so that'll be a 1, and a 0 and a 0 here, which will end up in a 0. So when we OR the value hex 20, or this binary number here, 001, 00000, into this number here, we will end up with a change of state here. So you can see this value here, this bit has changed from a 0 to a 1, and essentially we've illuminated the living room LED while leaving all the other LEDs the same. So that's a bitwise OR operation. Essentially, you can use it to set any bit you want in a register from a 0 to a 1. If it's already a 1, it'll just stay as a 1. So you can essentially force it to a true state or a 1 in that bit position. Next, we're going to be looking at a bitwise AND. Now an AND, because it's bitwise, again it does it on each bit in turn, but an AND gate, a 2-input AND gate, in order for the output to be true, both the inputs, both input 1 and input 2 have to be true. If either of the inputs is false or 0, then the output will be a 0. So we use the AND to be able to force bits off. So for example, we're going to AND in the value here in hex D7, which is these bits. So we've got 2 zeros in there. So this is bit 0, 1, 2 and 3. Bit 3, 4 and 5. So bits 3 and 5 are 0 in the value that we're going to AND in. So that's going to force this value and this value to fall to 0. If you do that on a bit by bit sort of way of going through it, the first one, we've already got a 0 here and we're ANDing a 1. So a 0 and a 1 through an AND, we're going to end up with a 0 in the resulting bit here. If we AND a 1 and a 1 together, we're going to end up with a 1 here, so no change again. Again, you AND a 0 and a 1, you're going to end up with a 0 result in here. 1, 0, we're now going to end up with a 0 in here, because if you AND a 1 and a 0 together, the result is a 0. So this one will change from a 1 to a 0. 1 and a 1 is going to be a 1 result here. And again we have a 1 and a 0, so the resulting value that's going to end up in here, if you put a 1 and a 0 into an AND gate, you'll have a 0 on the output, because it has to be both inputs to be true for it to be a true output. So this one will fall to a 0 as well. Again we've got 1 and a 1 here, so that will stay as a 1, and with a 0 and a 1 here, again that's going to stay as a 0. So if we have a look at the results on that now, so when we look at the results of the AND operation, the bitwise AND operation, we can see that these two bits here have fallen to 0, and essentially we've switched off the living room light and the landing light through doing that bitwise operation. Next we have an exclusive OR bitwise operation. This essentially will toggle the state from one state to another. So an exclusive OR, unlike an AND or an OR, an exclusive OR, if you have two inputs on an exclusive OR, the output will be true if either input is true but not both. So if you have both inputs as a 1 on an exclusive OR, the output will be a 0. The only way the output can be a 1 on an exclusive OR is if one or other of the inputs is true but not both of them. So if we go through and we're going to exclusively OR with this number here into our register, and we can see we've got 2 bits set here. So what this should do is invert these 2 bits here. So we should end up with a 0 and a 1 in here. So if we go through this like we have done before, bit by bit, a 0 and a 0 through an exclusive OR will result in a 0, no change. A 1 and a 0 will result in a 1, no change. 0, 0 will result in a 0. 0 and a 1 will result in a 1, so we will get a change here. A 1 and a 1 into an exclusive OR will output 0 because it's exclusive. It has to be either one or the other inputs that are true but not both. So a 1, 1 here will result in this turning to a 0, the output of the exclusive OR on a bitwise operation. And finally 0, 0 ends up with 0, 1, 1, 1, 0 ends up with a 1, and 0, 0 ends up with a 0. So the result of performing our bitwise exclusive OR is that these 2 bits have changed state, and essentially we've switched off the hall light and switched on the landing light in that one operation. So that's the exclusive OR. And if you think about the bits positions that we had on our previous diagram here, so the bit 0 was bedroom 3, the least significant bit, that has a value of 1 in hexadecimal, all the way down through bits 1, 2, 3, 4, 5, 6, 7 for the hall, living room, dining room, kitchen, and their hexadecimal values for their bit position. So in real terms, in C programming, when we are using this kind of bitwise operation, we could say, for example, that our switches, the state of all the switches, equals landing. In here That's bit 3 set, the hex value of 08. And that is essentially going to switch the landing light on and all the other lights off, because here we've assigned switches to the value of landing, and the value of landing only has one bit set in here, bit 3. So if we do this, all lights that are on will be switched off and the landing light will be switched on. This is the OR operator in C programming, and saying OR equals is the same as saying switches equals switches ORed with landing. So we do the OR equals here to shortcut that. So if we say switches ORed with equals landing, what we're basically saying is we want to OR the value of landing, hex 08, bit 3 set, into the current state of switches. The net effect of that is we will switch on the landing light. That single bit will get set, all the other bits will remain the same. If we take the current value of switches and we AND in the inverse, this is inverse in C programming, of landing, what that's going to do is it's going to take the value of landing, hex 08 or bit 3 set, and this invert will invert all the bits in that value for ANDing into switches. So essentially it will switch bit 3 off and all the other bits will be switched on. And when we AND in that value, essentially we're switching off any bits that aren't set in landing. So what we're doing, we're switching off the landing light and leaving all the other switches in exactly the same state. This is the exclusive OR operator in C. So if you take the value of switches and exclusively OR it with the landing value, essentially we'll be toggling the landing light on or off. Whatever state it's in, it will then change to the opposite state. Another example here, if you took switches and ORed in the value of landing ORed with haul, essentially this part here, landing and haul ORing together, would OR together bit 3 set, hex value 08, and hex value 10, or bit 4 set, to give you a hex value of 18. And when you OR that resulting value into the switches, you'll be switching both the landing and the haul lights on. So that is bitwise manipulation. There's a couple of other examples I just want to take you through, because bit positions can also be expressed as taking the least significant bit and shifting it a number of bits down the register, or from right to left, from least significant to most significant. So for example, if I was to say switches is ORed with the value hex 1 shifted left 3 bit positions, so instead of being bit 0 set, it's going to be 1, 2, 3, which would be bit 3 here, the 4th bit, and we're going to OR that value into switches. So essentially what we're saying there is it's the same as saying switches ORed with equals the value of 8 in hex, which is 1 bit shifted 3 positions to here, which has the value of 8 in hex. So that's the same thing, and that's exactly the same thing as we were doing before when we say switches ORed with equals the landing light, which has the value here 08 in hex. So hopefully that gives you a bit of a clearer picture of what's going on in embedded software or C programming when you're doing low-level bit manipulations. And just to finish this off, when we're dealing with configuration registers within a microprocessor and we want to set a bit or clear a bit to change the configuration of what the microprocessor is doing, those registers within the microprocessor are physically connected to the electronics built within the microprocessor, and when you set or clear a bit in one of those configuration registers, you are enabling or disabling certain parts of the circuitry within the microchip to enable or disable certain features and functions depending on which peripheral you're dealing with the registers for. So hopefully that's made it a little bit clearer as to what bitwise manipulation is for, and why we might invert bits or OR values together and AND them together. And the reality is all we're doing there is intentionally setting or clearing specific bits in a register that contains a value. And in the case of configuration registers, each of those bits has a function within the microprocessor. That's it for now, so I hope you're feeling well, and I will speak to you again soon. Bye for now.